All right, recording is rolling. Welcome to Monday, October 23rd. All right, so I got honors classes and AP classes. I'm just going to make all one video because not a whole lot of differences. And we're starting a new unit today, which is going to be energy. So summertime notes. Right. So everybody's got quiz regardless which class you're in. So thank you for turning that in. Right. A little bit different assignments. Gave you guys different things, I guess. Right. So one thing, one new page you guys have looks like this. It's got a bunch of new energy posters. Oh, hey, look, these are the ones hanging in front of the ceiling in front of me right here. Energy. If you flip it over, you see the blue ones on the back are all related to momentum. Those are the ones over there on that far wall. Now, these we won't get to for a couple of weeks, but here you go. You guys have them. You have energy and momentum going on right there. I gave you guys one of these stapled packets. Right? It's a giant table that's 3 pages long. Right? There's 4 rows there, 4 rows, 4 rows. A bunch of different scenarios that you can solve with this new framework that you guys can learn today. There's also some conceptual questions on the back. I think probably my honors classes will do a Kahoot on those eventually. Right? Right. And then you guys got some puzzles and different things going on in different classes. So my honors students get these chapter 10, 11 from physics principles and problems. AP, you guys get chapter 5 from college physics. I've circled 10 questions on each one. So those are the ones I'm eventually going to pick up from you guys about 2 weeks from now, about 2 weeks. Right, so those do not this coming Friday, but the Friday after. Right. Now, AP students, there's also in the next AP classroom I opened up over the weekend. So it's Unit 4 by AP's book. Right. So we're gonna have a new role on this. So how I've usually been doing AP classroom is you just do it, submit it, then I just give you credit for doing it. Okay. So let's add a couple of stipulations here. If you want full credit, then you have to get at least 5 right, and you have to spend at least 5 minutes on it. I think it's pretty reasonable, right? Because now I can see how much time you guys are going to spend on it. So get at least 5 right, spend at least 5 minutes. I think it's a pretty low bar to get full credit. So there you go. This is something. Right? Want to mention. Okay, I'm not going to be here tomorrow. You guys are going to have a substitute. There's an appointment got to take care of. So here's what we're doing today and tomorrow. Today, we're going to introduce you to this new topic, this new framework of thinking. This packet that you guys have is one of the things I gave you. Right? We're going to do 2 of these 12 rows, and then tomorrow do as much of this packet as you can, and then we'll eventually go over the answers. And if you can get the answers correct before I go over them, then that's a really good indication that you know like how this stuff works. How it works. Right? Right. Last note before we start on the actual notes. Right. This pink note here at the bottom. Right. Energy and momentum unit in-class quiz end of November. Here's how this is working. So we'll do energy for the next couple of weeks. I'll give you one of these take-home quizzes like I've been doing all along. Right. Then we'll switch over to momentum for a couple of weeks. Same thing. I'll give you guys a take-home quiz. Right. Now the schools having common classes do common assessments. So for example, there's 4 different physics teachers going on in the school. Four different physics teachers. And so we all got together. We came up with a common assessment to cover both these topics. So energy and momentum. Right. So that's all ready to go. I mean, it's we checked it out. It's all the stuff that you will learn over the next 4 weeks. So to keep this fair for like all 4 different teacher classes, this will be a traditional quiz like in class closed notes. So you guys will actually take this quiz in class. Okay. All right. So you guys good with what's going on? All right. Here we go. Notes time. Right. So I'm gonna switch back and forth between writing some notes and throwing some of these posters up here. I want to start big picture, right? Because you guys know there are lots of different types of units in this class, like maybe meters could measure displacement, kilograms could measure mass, some kind of newtons could measure a force, a push, a weight, right? And now we're going to switch over to this new quantity, this new way of thinking, energy, which is going to be measured in joules. That's what it's going to be. I'll write that down here in a minute, right? And what are we going to do with that? Well, there's going to be this really important framework that energy is conserved. This says the sum of energy initial equals the sum of energy final. Right? Right? There's a whole set of problems that you can solve. Sometimes, like this is the best way or the only way to solve it. Some ways, and by the time you guys walk out of class today, we'll set up and solve at least one problem where you can solve it using past methods from this class, but you might say like, oh, it might be faster to solve it this particular way. Right? It's a certain way to think of it. Right? This says energy is conserved for a closed system. You can even rope off, let's say, the observable universe and call that a closed system, in a certain sense, right? And if you look at like how much energy there was a billion years ago, it's exactly equal to the quantity of energy that there is today. is exactly equal to the quantity of energy that there is like a billion years from now, right? So, or how about this? You put some gasoline in your car and you drive at a certain distance, right? That gasoline's like making the car go, right? There's a certain amount of stored energy there, right? But it only gets you so far. Now, where did that energy go? Well, move the car. Maybe you're like driving up hills. Maybe there's some friction loss pushing against the air. Maybe it heats up the engine, right? There's all these different places the energy can transform. It can take different forms, but the quantity of number of joules of energy is never goes away, right? Then you're on a gasoline, you need to fill up the tank again, right? Or there's a battery that has so much energy. A AA battery won't last forever, right? Or you have to eat lunch, and then you use your energy to like move and think and blah blah, blah, right? And then you need to right, so like food calorie stuff, right? Okay. Okay, so that's energy being conserved. That's if there's no energy entering or leaving the system, right? If you have an open system, well, we're going to tweak that a little bit. We're going to say, well, you might not start off with some sum of initial energy, right? But maybe there's plus or minus some energy that's entering or leaving the system. And a transfer of energy, the term for that in physics is just called work. Anytime you see work in this class, we're talking about transfer of energy, right? You have some initial energy, you add or subtract energy, and you maybe with a different amount of energy at the end, right? Now, these two terms here, closed system, open system, AP makes a big deal of these. I think these terms may have come up a couple times in the past, but with these new units, energy and momentum, you'll see these all over the place, right? So different ways to define these. If it's a closed system, there's no energy entering or exiting the system. Another way, another definition type you might see is something like there's no external force or no net external force, or right, pushing for some distance, something like that. Okay, so there you go. There's a big picture right there. All right, now energy can take a bunch of different forms. Actually, I have two posters that are kind of similar to each other. I don't know if I'll consolidate these two, but we kind of go back and forth here. Right. And so variable, what's it called? What's the unit? Right. All right, we've got here energy just in general could be some number of joules. Got to write some notes for you guys too. I'm just got my notes ready, gonna copy these down as we go along. Right. Work, now capital W as a variable. First work, right? That's just a transfer of energy, so it could also be joules, right? Now, energy could take all these different mechanical forms, and there's also a bunch of forms that are not on this table, like thermal energy or nuclear energy or chemical energy stored in a battery that we're not going to so much touch in this class, right? But these forms, like energy position or energy motion, might care more about, right? Some do with rotation here, right? Now, near the bottom of this table, I got P, power, and watts. I'll write this also on paper, right? Power is a rate of energy, right? So it could be like joules per second, right? Now look real close. I see capital W two different places on this table. They mean two totally different things in two totally different contexts. Capital W is a variable, represents work, which is measured in joules, right? If you see capital W as a unit, that means watts, and it can quantify how much power, which is like joules per second, right? These two very bottom lines these blue lines relate to momentum, which we're not going to talk about for a couple of weeks, so don't worry about that so much. It just wasn't enough to make its own poster, so this would throw on that one. Okay, to give you guys a bit about this unit joule right here, and then we'll switch over and start looking at these forms of mechanical energy. Okay. So something about joules, right? So we got energy, which I should say is a scalar quantity. Right, so in contrast to a vector, right? So directions aren't going to really matter. For that matter, you probably won't see time mentioned hardly ever for the next couple of weeks, right? Time doesn't show up as a unit, right? For energy, right? And it's measured in joules. So what is 1 joule? Right? We can kind of get a hint from, maybe I should flash this next poster up here. You can kind of get a hint from what work is. If you push something for some distance, right? That's a transfer of energy, right? Or hey, what if I lift something for some height? Like I've got a 1 kilogram mass right here. It takes 10 newtons to lift it. So it takes 10 newtons because it weighs 10 newtons. So it takes 10 newtons to lift it. Suppose I lift 10 newtons, 1 meter, right? Lift 10 newtons, 1 meter. Ooh, I did 10 joules of work. I transferred 10 joules of energy, right? Came from my muscles, right? I had to like eat some kind of nutritional value, something, and then, right, I got this energy stored in my muscles, and then I lifted, right? And if I lift 10 newtons, 1 meter, it takes 10 joules to do that. But look at these variables, and you can get an idea exactly what 1 joule is in terms of units. Right, guys? Force is measured in what? Newtons, right? And distance is measured in meters. So if you multiply 1 Newton by 1 meter, that's the same thing as 1 joule, right? But Newton, you guys know itself is like a positive unit, so I can like break that down. You guys remember Newton's second law of motion? F equals ma. Oh, so Newton, that's right. It's 1 kilogram meter per second squared, right? Multiply that by this meter. Oh, and that meter could go together. So 1 joule, capital J joule, we see in this class, is 1 kilogram meter per second squared, right? That's how it breaks down in terms of SI units, right? Sorry. Yeah, thank you. Good catch. Thank you. Yeah, thanks, Steve. Yeah. Good call. Yeah. 1 kilogram meter squared per second squared. There you go. I know it says before, let me reiterate this point that however many of these there are in a closed system, or even just like the observable universe, is the same as there ever will be in that closed system or observable universe, right? However many of these units there were, crazy number, right? Like a billion years ago, same as there are now. Right? Now there are different ways to quantify energy. We're mostly going to do joules, but let me just throw a few up here, a few other ones that you might see out in the wild. Right? So if you ever hear anybody talk about calories, right? I think it's the amount of energy it takes to raise 1 gram of water by 1 degree Celsius, something like that, right? You can translate in terms of joules. I think there's a conversion factor of like 4.18 or something like that, right? But that's a way to express energy. I've seen something like a British thermal unit. I've never actually solved a problem that ever deals with that, but I've seen that term thrown somewhere, right? But a common way that you probably will see, like if you guys get an electricity bill one day, do you guys know how energy is quantified on your electricity bill? It's like kilowatt hours. Yeah, right. So kilowatt hours, right? So kilo is 1,000 or something. Okay, yeah, watt is a rate of energy, like energy per time. Oh, and then hours is time. So if you do energy per time multiply by time, they get you to some quantity of energy, right? Me personally, if I was come up with this system myself, I would probably just charge for megajoules, but kilowatt hours kind of stuck around as standard, so that's what we got. Speaking of watts, let's switch over to power because that's the other variable that's new that might pop up the next couple weeks. Power. All right. Power I've seen as either energy per time, or you could say work per time. Maybe I should say work per time. I've seen both of these. Right, so some version of that. And work is just a transfer of energy, right? Right. Oh, and you can see what the unit's going to be because there's joules, there's seconds, right? So power's measuring. What's the unit for power again? Watt. Yeah. So I'll do capital W for watt. So like 1 watt, right? It's the same thing as 1 joule per second, right? Which, if you like, is the same thing as, well, joule is this here, kilogram meter squared per second squared. So if you do that, hey, that's like 1 kilogram meter squared per second cubed, right? Same thing, right? So when you guys look on a light bulb, right? Suppose you got like a bulb here, right? It's got a little filament or something, right? And suppose it has printed on it 40 watts, 40 watt light bulb. Right? Oh, well, what that number is telling you is the rate that that bulb is drawing energy, right? Maybe if you have it plugged in a flashlight, it's pulling from like some AA battery at like 40 joules per second, right? Maybe if it's plugged into the grid, right, pulling from the grid like 40 joules per second, right? And then the longer you leave it on, right, it's like either draining the battery or you have to pay the utility company more, right, for the energy that they're delivering, right? Something like that. And from the energy company's point of view, right, they have to supply this energy from somewhere. They always have to dig up like more coal or more nuclear or maybe like find a waterfall or something where there's like hydroelectric, right? There's some kind of motion going on, right? Some kind of height change, some kind of motion, right? It's got to be some source of that energy, right? You can't just have like one lump of coal and then run a power plant forever, right? Because this energy is like finite and it's conserved. Right? Right? You guys good so far? All right. So let's go back to here. So energy's gonna take one of a number of forms. In this class, we really care about forms of mechanical energy. Because I'm saying mechanical. So we're not so much interested in like thermal or nuclear or anything like or chemical, right? It's just these handful here. And in fact, if you just focus on the yellow rows, that's mostly what you care about. The green rows, I'm going to talk a little bit about, but most care about those, right? So energy can take these forms. And remember what this is all plugging back into. Right? You guys will see it before you walk out of class today. It's all plugging into like one of these. We're going to set up equation. When I say the sum of energy initial, sum of energy final, I might just go shopping for different versions of these and then set up equations from that. Say, okay, well, all the energy, what's this kind of energy? Now it's that kind of energy, right? So let's go down the list here, right? So I know work is something to do with force times distance. If I push something for some distance, I've transferred some amount of energy to it. So term for that is work. I can quantify that in joules. Right? Right. Hey, how about this though? This is going to lead straight to this next one. Right. Let me break out this example I just said a minute ago. Right? If I lift something for some height, well, the lifting force has to be equivalent to the weight if I lift it at constant speed, right? And the displacement would be vertical, which would be a height change. So it's kind of like if I lift it, it's like, well, where's that energy going? You could think of it sort of like as going into the object. So if I set this on the shelf, right, now it's got like all the stored energy, right? And you can quantify that exactly like this, like mgh, right? Where mg kind of represents the weight of the object, and h, well, that's the height unit. That's like a vertical displacement. You guys see how mgh is kind of a specific form of force times distance if you just lift it straight vertical, right? Right. So let's do notes on this one. Yeah. Okay. Yeah. So let's look at the posters, I guess. Do the posters. Okay. I'm going to come back to this. I still got to hit these, but let's just do one at a time as we're going on. Right. So work is force times distance. Whenever you see a force versus distance graph, or you guys see lots of graphs in this class. Every time you see a new type of graph, I think this one's pretty new. Well, kind of saw a Hooke's law version of F versus X, but right. On the AP exam, you see these graphs. I mean, you're going to on the AP exam see number of these graphs, F versus X, and whenever you see F versus X, the first flag thinks in my mind. So I wonder if they're going to ask some kind of work or energy question. Okay, so I wonder if this can be this to do like the area under the curve. If it's a constant force, then you have a rectangle shape. You just do force times distance, area of a rectangle. Okay, all right. Let's look at a specific version of this because I want to figure out something that would be easy to overlook, but actually means something. You guys see that dot right there? Right. That's actually a special kind of multiplication. It refers to a dot product. What it means is you only multiply the parallel components. Okay, so this gets a little trivial at first, but if you think deeply about it or you run into a bunch of problems, this makes more sense why that has to be a dot product. Right. So if I take 10 newtons to lift this, it takes 10 newtons to hold it up. Right. If I bring it up, right, it takes more and more work to lift it. But if I just apply an upward force of 10 newtons and I carry it horizontally across the room, I'm not actually doing any work on it right now because the direction of the force upward and the direction of the motion, like the displacement horizontal, right, has nothing in common with each other. Right? So that dot product means you only multiply the parallel components. Right? So let's look at one that's a little bit more complicated. Right? Yeah, this poster, after I put it together, I'm like, I'm kind of iffy about it because at a glance it looks a little complicated, but if you like just kind of breathe this in and look at this for a while, it does make sense. I want to convince you here. So let's say we've got an object here, right? And okay, this object has some weight, mg, and I'm going to lift it. I'm going to walk up these stairs as I'm lifting it, right? So I'm lift. Oh, I need to pick up. I need to apply an upward force that balances out the weight. So this force is equivalent to the weight, isn't it? Right. As I'm walking up the stairs, remember, none of the side component adds anything to the work, right? Because the direction of the force and the side motion has nothing to do with each other, right? But the fact that I'm going up the stairs, this upper component, does matter, right? Right. So how much work did I do, like lifting this object to the top of the stairs? Well, it's this upward force that I'm applying times just the vertical height change, right? Which is this weird like diagonal distance times cosine of this angle between the two vectors, right? Could be d cosine theta would be a height change, right? So the total work then would be F times d times cosine theta, right? Oh, that's what this dot product is. See, work is force dot distance. And that's usually defined this way, right? For the magnitude of the force times the magnitude of the distance, like this whole diagonal, right? Times the cosine of the angle between the two, right? Now, this is the angle between those two vectors, right? Careful, sometimes they give you like the angle up here, in which case this cosine turns into a sine. So just watch for that, right? But don't always assume cosine, but if it's set up like this, it's cosine. And usually textbook is defined as cosine, right? Is that okay? All right. And then here's a horizontal type example, right? What if you're pushing a shopping cart? Now, if I make this really simple, if you just push horizontally for some distance, then the work you put into pushing the cart is just very simply force times distance. That's it, right? The one I actually listed up here is a little bit more complicated, right? Because you're not actually pushing straight forward, you're actually pushing like down and forward. But only the forward component of that pushing actually goes to moving the cart forward, right? Like the amount that you push down has nothing to do with its motion, right? So I can say that the work I did pushing into the cart is F push times cosine theta, playing off the single theta, right? Times however far the cart moved, right? Got a question earlier today. Does it matter that this cosine or sorry, this angle is negative. You guys know cosine of 60 degrees is 0.5. Cosine of negative 60 degrees is also 0.5. So cosine of a positive or negative angle makes no difference. Okay. So a little side thought there. You could add on to the story. There's a textbook question that's similar to this. So you could add to the story. You could say, well, if I'm pushing kind of down, I bet the normal force is more than the weight because the normal force has to carry both the weight and also the amount I'm pushing down. I bet this friction force, this coefficient of friction times that normal force, and maybe the friction force is doing negative work on the cart to push it forward. So this negative force for the same distance, right? In fact, if the cart is not changing speed, then I bet whatever your work you're putting into it is exactly taken out by the friction. So you're pushing it down the aisle. Suppose you put in 100 joules moving forward. So some force, some distance, 100 joules. Right? There you go. Right. I bet this force times that same distance, right? If these two are the same magnitude, it might pull out negative 100 joules work done friction. Yeah.
Why is the normal force so much bigger than weight?
Yeah, why was the normal force greater than the weight? Because if you're pushing kind of downish, if you break that into components, see how the amount that you push down, right? Like suppose the cart itself weighs 20 newtons, and you're pushing down with an amount that it comes up to like 30 newtons. This 20 down, this 30 down has to be balanced. The floor has to push up with 50, right? 20 down and 30 down balances 50 up, right? Like imagine from the point of view of the floor. What if the floor was like a giant scale, right? If the cart's just there, it reads some weight. Right? But if you're like pushing down on the cart, it's gonna read more. Okay, normal force. All right, so we got that. All right, now, right. So this guy right here, this MGH. Okay. So now we've taken some weight, we've carted it up the stairs. Actually, I'm just gonna flash these notes from earlier. So we do this. Let's kind of talk about this. Right. So we got this mass. We're gonna lift it up these stairs to some height, right? And then like perch it on the edge, right, of this like cliff, right? Or I've got this just at the edge of this table right here, say like 1 meter above the floor, right? So supposedly it has potential energy equal to mgh is what I just gave you, right? Now that's energy that here. What if there's a little breeze that came across it, right? This thing just loses balance, like crashes into the floor. I bet there's a bunch of energy that's associated with crashing. Right? How much energy? Oh well, yeah, it's equivalent to this because this could be like a closed system energy could be conserved, right? So when I first learned this, maybe this side thought that maybe it's one of these things that could help you figure this out, is I was not 100% convinced this was even meant anything useful the first time I learned this, right? Here's why. I said, well, what if you like dug a hole in the floor? Like we're on the second floor right now. Like if I dig a hole in the floor, right, this lab weight here is like perched on the edge of this table, right? If it falls and hits the floor, right, it fell 1 meter. But what if it falls through the hole? Well, now it's going to fall like an additional 3 meters down to the floor below. So like, what's the height change? You know, it just depends like whether it falls through the hole or not. It has different amounts of potential energy. Right? Now, after I solved lots of these problems, I realized what's actually going on. You're allowed to define floor height 0 wherever you want. And as long as you're consistent within a problem, it's okay. So if you define the floor height 0 right here, and it falls through the hole, now it's just going into negative height territory, and you'll get negative values. But if you solve for like what's the crash speed at the end, that's one thing you can do with conservation of energy. You can solve for crash speeds. Okay? That's okay. You'll get the same thing as if you would define the floor all the way down there, 3 meters down to start with. Okay, so that's right. That checks out MGH. Okay. Now, okay, you guys good so far? So far. All right, next line. Now this one's green. This is a bit more technical. I don't think AP is going to ask you a question about it, but this might show up once or twice, so it's worth mentioning. Some of you guys might look at that MGH because this leads to this, right? And say, well, hold on a minute. That G, like at the surface of Earth, might be 9.8 meters per second squared, but that's only at the surface. I remember from the last couple of weeks, if you dig a tunnel too deep, or if you go up a building too tall, or like take off a rocket, right, that G will get smaller either way, right? This is only true at the surface. So now, even if you go from the top of Mount Everest down to sea level, okay, that change is so small you can just still use MGH, right? So pretty much all practical problems in this class are using MGH, right? But if you want to like send a rocket to Mars, that's going to be changing. Maybe you need a different way to think of potential energy. There's a more universal way. Now, it's weird, it's negative. I'd like to talk more about this now, but I think if I talk about this at all, I'll probably save this for another day, like why it takes this form, right? Got like universal gravity constant, the mass of the planet, the mass of the object, the radial size of the planet, right? A couple things I'll say is, yeah, this is useful in deriving escape speed is one use for it, right? Another thing is, if you find two slightly different values of R, and think from the top of Mount Everest down to sea level, like to us, that might say, ooh, that's a huge height difference, right? But from the point of view of the radius of the Earth, it's like tiny, like proportionally, right? Right. If you use two slightly different radial values, you can show that this green line actually simplifies to just MGH. Okay, so yeah, that is doable. I might do that in class one day. All right, good so far. All right, now let's take this force times distance and apply it to springs, because you can store energy in springs. I got some springs right here. Right, so if I pull with some force, it stretches some amount. I pull with twice the force, it stretches twice as much. Pull with 3 times the original force, it stretches 3 times as much. Isn't that a linear relationship? Doesn't that make sense? Right? This is scaled linearly, right? 2, 4, 6, 8, 10. Right? Okay. So let's make a graph here. It's graph time. Okay. Let's see what you guys remember from this. Get my notes straight here. All right, graph time. All right, you guys making a graph in your notes. Graph in your notes. Okay. So here's the premise: is I got some spring. Okay. I'm gonna. You could compress or stretch a spring. Since I got stretched springs in front of me, I'll just go ahead and stretch a spring. I got some force, an equal and opposite force from the Newton's third law. Right, like it's going to stretch at some amount. I want to say, what's the relationship between what force I'm putting on it, say in newtons, and how far it stretches, say in meters, right? Something like that, right? You guys should know what this graph looks like. I'm going to take a quick trip around the room and see who remembers what this graph looks like. That spring scale. Who's going to get this graph? All right. Who's going to get this graph? All right, Reese got it. All right, Eli's got it. Addie's got it. Melissa's got it. Catherine's got it. A bunch of guys get it. I probably missed a couple of guys too, right? A lot of you guys drew this right here. Bam, that's what you do, right? And there's a name for that. It's called whose law?
Hooke's law.
Hooke's law. That is Hooke's law, isn't it? Hooke's law, right? Oh, and there's a formula that goes with that. What's that formula? F equals kx. You guys remember F equals kx? Yeah, or yeah, some textbooks do negative. Like this blue one, little tiny force stretches no problem. That's a really small spring constant. The brown one's kind of like the Goldilocks. Ooh, it feels some resistance, kind of medium, right? And this gold one's like really stiff. I put a huge force, really stretches off. So huge force barely stretches. That's like a really steep slope, right? So these different spring scales can have different slopes. So the slope of this, I'll call K for the spring constant, right? Now we're interested in something else because I remember back right here, area under force versus X represents work. Oh, I bet I took some energy to stretch the springs, and I bet some of that energy is stored in the springs. Let me give you guys another spring example while we're thinking about this. This ballpoint pen right here, it's got a spring in it, right? Right here, right? Spring. So if I pull this apart, I push the cartridge, smash it. Okay, now I have a compression example, right? Let's go. Right, this thing's gonna fly out, right? It's gonna have the speed, could have some height, right? Where did that energy come from? Well, at some point it was stored in the spring because it took some work to compress it. Okay. Hey, is that still the area under this curve? Area under this curve right here? This area right here, isn't it? Right? Suppose you stretch it some general amount x, and the amount of force that it took to do that would be equal to kx, wouldn't it? That's Hooke's law right there. That was kx, right? So is this area right here the work done on it, and therefore the energy stored in the spring? I'll call it capital U for potential energy. I'll do subscript S for spring. Right? That's 1/2 base height. The base is some general amount x. The height is the resulting kx. The force that would have caused that. Right? Oh, and those x's you can combine. Now we're getting the energy stored in the spring is 1/2 kx squared. Right? So remember, the tricky thing about springs with work is that the force is not constant. The force is increasing with like the more you stretch or compress the spring. Right? So like that, right? And then the energy ends up being that expression right there, 1/2 kx squared. Right, guess that. The energy stored in the spring. If you know how stiff the spring is and how much you stretch or compress it, you can know how much energy in joules is stored in the spring. Right? Everybody good? Right. So that's this guy right here, spring potential energy. Right? U sub S, 1/2 kx squared. Right. And let's connect that to, let's bump these here. Right. Oh, look, that's Hooke's law. Right, it's got an orange banner across the top because you guys saw this one a few weeks ago. F equals kx. That's the graph you guys just drew. And oh, look at this. Look at this. Hey, energy stored in a spring, 1/2 kx squared. It's been down there the whole time. I just didn't really make an effort to point it out last time because it wasn't relevant then, but it's relevant now. Energy stored in the spring, 1/2 keg squared. Right? Yeah. If you like 1/2 base height. Right? All right. You guys good so far? All right. So, right, covered all these. Right. One main last one that you care about, and then another slightly different version of that. Right. Kinetic energy. This is energy of motion. Right. So if something's in motion, it has energy. How much? Well, it depends on its mass, depends on its speed. Remember, I told you guys that energy is a scalar value, not a vector value. Right? So I don't really care about the direction motion. I only call it velocity. I always call it speed. Right? 1/2 mv squared. Right? So I was trying to figure out like what's the proof for this? Like what's the derivation? One way you can see this true is we'll set up some problems like by the end of today where you say, well, there was an old way we used to do it, and then with this new method, and oh, hey, look, they end up being the same answer, so that must be true, right? Also, I don't know. I try to find in a textbook some proof of this, or find it on the internet. I have trouble doing that, but here's my best shot. I'll just flash this. I just kind of made this up. I don't know. I didn't actually find this anywhere. Right? But if you made a graph that was like momentum versus velocity, right? Now momentum we haven't talked about yet. It's just mass times velocity. That's all it is, right? This would have to be a linear relationship because if you like triple the speed, you're going to also triple the mass times speed, right? Something like that. Right? Has to be linear. And the area under that curve I know would have units of joules, which would represent some kind of energy, right? And if you run the math on it, it's similar to the Hooke's law graph that we just did. It comes out to being 1/2 mv squared could represent energy, right? So okay, so if something has momentum, it does have kinetic energy because they got the same like ingredients, right? The mass and the speed, right? Mass and velocity. Right? And so anyway, one or another, that's going to be our term for kinetic energy, energy motion, 1/2 mv squared, right? And finally on this list, energy that's rotational. This is like a green line. So this is mostly might come back in December. Okay, in December this will come back, but otherwise we're gonna kind of ignore it from there. But look, it's a really similar looking expression, right? So like, what's the energy of like a rotating tires, right? Instead of mass, now it's rotational inertia. Instead of linear speed, now it's angular speed, radians per second. Right? But otherwise, it looks pretty similar, right? Here, I will give you guys an example where you might see this. Is do you guys know what a Pinewood Derby car is? Pinewood Derby car, right? These little wood box cars that come in these little boxes. They're about this big, right? They used to be in the Scouts, and we get one every year, and you like cut it and sand it down and paint it and pop on the wheels, right? And then we race this thing. So you got these racetracks that, and it was put these cars at the top of the tracks and let them go, right? And they'll like race down, right? So who's the long first, right? One of the biggest tips to win that race is, well, those cars are on like 4 wheels, right? If you take one of your axles and bend it up so that it doesn't actually touch the track, now the car is resting on 3 wheels, then there's a lot of energy that's not going in to make that 4th wheel rotate, which is not going here. So all the other cars, we got like 4 wheels that are taking this energy, right? In your car, if you bend up a wheel, now yours is only 3, 1 stagnant, right? Those cars always win the race because you have excess energy that can go into translational, so they'll get to the bottom first, right? Right. So got that. Okay, let's do yeah, let's do an example, a classic example here. Okay. Here. Let's use this poster to guide us. All right, so quick recap. I said we're going to solve a bunch of physics problems with something to do with one of these. Right, we'll start with just a closed system. Energy is conserved if you add up all the energy that's before and after. And then you can go equation shopping and say, well, maybe I want one of these forms of energy, probably focus on these 4 gold boxes right here. Right? And you can craft equations that then you can use to solve stuff. That's pretty much like in a nutshell what this next 2 weeks is all about. Right? So let's do a really fundamental example right here. Oh, look at what we have. Galileo drops the ball from the Leaning Tower. Right? How many times does the story come back to this class? So now we're going to use, well, we need to figure out, here's the question. How fast is this ball crash landing? What's the crash speed? Right? How fast is it bam about to slam to the ground? Right? Which, you know what? I think you guys already know a way to solve this problem. Do you guys know a way to solve this problem already? Yeah, you guys remember? Hey, it's the 3 amigos. You know, if you know the height of the tower and you want to know the crash speed, which one of these will lead directly to the answer? First, second, or third? Third, yeah, the third one, right? You could use the first 2 system of equations and substitute through the time. But if you know the height of the tower, bam, that's right there. One, the crash speed, bam, that's right there. Right? Let's use the third one. So we're going to solve this 2 different ways. We'll solve it the old way and we'll solve it the new way. Right, so we got Galileo's tower. Right, we got some ball falling. Right, there's some height change going on right here. Call it H. Right? There's the old kinematic way to do it. Kinematic. Right? And there's going to be the new energy way to do it. But I mean, if physics is all self-consistent, they should lead to the same answers, right? So we're going to find out. So let's do Vf squared equals V naught squared plus 2ax, right? We're solving for Vf. Now, if you drop the, I mean, if you throw it, then V naught something. But if you just drop it, then doesn't it just go away to 0? So what we're solving for squared is 0 meters per second. Then square that plus, instead of 2ax, I'll call it 2gh. Is that okay? Gravity field's a type of acceleration. Height change is the displacement in this case. Right, in this case. Right, this piece goes away. Right. Oh, and then the crash speed, we got it right here. So here's V final, like the crash speed. I got V final it's just the square root of 2gh, right? Which is something that you guys have seen before, right? You guys have seen this before. Hopefully more than once in this class, I think. Right? Does that look familiar? I hope that looks familiar. Right? I think I may have mentioned, I recommend you hold on to that expression in your back pocket, because if there's any kind of height change, you want to know anything about speed. Right? Later on, there's an example with a pendulum. It's going to be a little bit different form of that. Right? Square root 2gh. You see that all over the place in physics. Right? Got a water tower spurting water out the bottom. How fast the water spurting out? Square root 2gh. Right? It's a different method you get to, but it needs to be the same answer. Right? Now let's do a new approach. Right? Conservation of energy. I'm going to I need to define the system. I'm going to define the system as the ball Earth system. Okay? AP makes a big deal about identifying what's in a closed system if it is a closed system. Okay? So we got the ball, obviously, it's changing speed, so I need to focus on that. But the force that's causing it to do that is from the Earth, this gravitational pull of the Earth. So if I don't include the Earth, then that force would be external and it would be an open system. I'm going to bring in also the Earth. Right? So the ball Earth system. The ball and the Earth are pulling on each other. Right. And then I can say this right here. Here's the framework. It's like the first domino that's going to knock over this whole process that should lead us to this particular outcome. Okay? The sum of energy at the top of the tower equals the sum of energy at the bottom of the tower. Of course, we're going to ignore air drag like we normally do in this class. Okay, here we go. Here we go. So first one you guys are solving. Maybe I should ask you guys, what type of energy do you think the ball has at the top of the tower? Gravitational potential energy. And what's the expression for that? MGH. Yeah, MGH, right? So just if you watch this video at home, all you do is you go equation shopping here, really just focus on these 4 gold boxes, say, oh, well, it's energy to height, MGH, boom, that's it. Right. And what about at the bottom of the tower? Like 1 nanometer above the ground, the ball has all what type of energy? Yeah, kinetic. Inertia 1/2 mv squared, right? And nothing else. I mean, it doesn't have any height. There's no springs lying around, right? It's all 1/2 mv squared. Right? As long as there was no air drag losses, that would be the case, right? Yeah. Right. Oh, what cancels out on both sides? The mass of the ball. Hey, wasn't that the Galileo story to begin with? If you take that and that, you drop them in the tower, will they fall down side by side? Yeah, the same kinematic motion. Yeah, so the mass should cancel out. Okay, that's a good sign that we're probably on the right track. Right? We're solving for this speed at the bottom, right? V final. I cross multiply the 2, so Vf squared is 2gh, right? And then square root both sides. The crash speed is, oh, look, there's a square root 2gh, square root 2gh, right? Just like that. Bam, bam. Okay. Oh, look, it's a match. It's the same thing, right? So 2 different approaches, and they lead to the same thing. Right? So now we've got a really powerful new framework for solving physics puzzles, right? And sometimes this energy method will solve something like way faster with less paper and less time than previous methods. You're like, okay, well, I could have solved it using, but this way's faster. And sometimes this is like clearly the best way or like the only viable way. And, okay, so depending on the question. Okay. All right, you guys got that? Good so far? All right, I think we're off to a good start here. All right. All right, stop this. Let's see what I got lined up next. Ooh, this next one's pretty fun. All right, so, I've defined the system here. This is going to be the block spring Earth system. So here's the scenario. I got this block that has some mass. I'm going to smash against a spring. Right. The spring has this stiffness K. I smashed it. This displacement X. Now it's like spring loaded. You guys see it? And let it go. It's gonna fly around that loop, right? And okay, so there's no frictional losses. Well, let's get rid of that. Right? And oh, this loop has some height. Right? I bet slowing down as it's going up some height, right? And it probably has some speed left over at the end, right? Maybe at the top of the loop. Notice all these energy problems. We're going from some initial point to some final point, right? Point A to point B, initial to final. Right? Where's the energy here? What's the energy here? And we could set up equations and then solve for that. A good question for this one might be, well, what is the speed at the top? That could be a good question, right? Can you guys think how you would set up an equation to solve that? And I have the answer just covered right here. Okay, so go ahead and write down your notes. What do you think the equation setup is for that one right there? Can you write an equation? Give you guys a hint. Here's the first step. Bam. I got a two-step setup. I didn't actually solve it. I just did the setup here. Okay. So there's your framework. Energy is conserved in a closed system. Right? Got the block spring in the earth. I got the block because I'm focusing on the block changing speed. I got the spring because at some point the energy was in the spring. Actually, at the very beginning, it was all in the spring. Okay? And I have to include the earth because there's a height change. The fact that it rose some height. Right? The higher it goes, but slow it down because Earth's gravity is pulling it down. Right? So I've got a block spring earth system. I don't have to include the track because there's no friction. And the force from the track, there is a force on the track, but it's always perpendicular to the motion. So for that reason. All right. Gotta move along here just to beat the bell. But did you guys come up with, or I should ask you guys, initially all the energies in the spring, and you guys would say gonna go 1/2 kx squared because that represents the amount of energy stored in the spring. There's some number of joules there. Maybe you run the numbers like 100 joules, 100 joules. I'm just making up something, right? 100 joules. Right? Then by the time it gets up to here, it's like the final location, the energy went to two places. Where and where? So lifting against gravity, and the term for that's going to be mgh. Right? And whatever's energy is left over, hopefully there's some left over. You guys remember it has to do with speed. It's going to fall off the track. There better be some speed here. Is what type of energy is that? Kinetic, 1/2 mv squared, right? Notice you can't just say like h plus v or something. Remember, anytime you add or subtract terms, they always have to be in the same unit. This is some number of joules. This is some number of joules. This is some number of joules. Maybe my initial 100 joules turned into like 20 joules here, and the other 80 joules would left over there. If you know the math, you can see a little bit of algebra and solve for that. That could be one way to do it. Okay.
When you have to add the kinematic energy to your equation, you just know the difference in stop.
Yeah, if it's in motion, then there is some of this kinetic energy. Yeah. So kinetic energy if it's in motion. Yeah, there you go. All right. Look at one more poster real fast. Car brakes to a stop. I'd like to go this one in more detail than I have time for, but car brakes to a stop. Now, this is a really classic physics question. This is an open system. This is, I'm just going to focus on the car. Notice the setup here is a little bit different. There's some initial energy, maybe kinetic energy of the car. There's work done by friction force, and then the car maybe comes to a stop, something like that. So this is how it works out in the end. Again, ooh, that's an interesting proportionality at the end. You guys see if you triple the speed of the car, you're actually going 9 times the distance. Right? So I do want to make a big point of that, but since we just got a little time left here, tomorrow, do as much of this table as you can. We're going to do, let's do a couple of rows here today. So very first one. Oh, Galileo drops the ball from the top. Hey, we just did this one. So what's in the closed system? I got the ball and the earth. Yeah, there you go. The ball, I'm going to call it the ball earth system. Energy at point A, mgh. Energy at point B is all 1/2 mv squared. Okay. Solve for VB. So I got sum of energy at point A equals the sum of energy at point B. mgh at point A equals 1/2 mv squared at point B. And if you solve for that VB, you get VB is the square root 2gh. That's a really classic fundamental physics example right there. That's probably a good one to start with. Okay. All right, I'm going to do one more with you guys. So I'll have time for today. All right, you guys see this spot? Oh, look, car brakes to a stop. Now, it should say that all 12 of these examples are closed systems except for these two. So actually, it's 10 closed systems and 2 open systems. I need to modify this table, but everybody do this. Divvy these 2 cells right here. I'm going to say work and work, right? Because these 2 are open systems. These 2 are open systems. Everything else is a closed system. Okay? So what's in this open system for this car braking to stop is just the car. I'm not going to include the earth because there's no height changes. There's no hills that's going up or down. Right? I'm not going to include the road, even though there's a force from the road. I'm going to treat that as an external force, which is going to make it an open system. Okay. All right, so energy at point A. Well, the car was in motion. That guys, was what kind of energy? Kinetic. And what's the term for that expression? 1/2 mv squared. Right? Ooh, guys, is work force times distance? Is that the friction force times the braking distance? Right? And I should subtract, right? Minus friction force times the braking distance. Right? If you want to make this more fun, you can say, well, how's that friction force related to the normal force, related to the weight of the car? It might involve this mass, but we're going to write that deep, right? Today anyway. Right? And then when the car comes to a complete stop, it says the word stop. Guys, what's yeah, zero. There's zero kinetic energy because it's not moving. Zero potential energy. Hasn't gone up any hills. I don't see any springs. Yeah, right. And then I have a universal question on this table. What's the speed at point B? Which in this case, the answer would just be what? 0. So this is 0 joules. This is 0 meters per second. A better question for this last scenario, though, would be, what is the braking distance? That's usually what you'll see for this question. Car brakes to stop. They give you all these values. What's the braking distance? And then you guys know for AP, you're more likely to see a proportion type question. And this is a really good proportional question right here for a car brake to stop. So like for sure that's gonna come back in this class, right? Yeah, all right. Oh, I beat the bell by 30 seconds. How about that? How about that? All right. So yeah, thank you everybody for your quizzes. Tomorrow do as much of this table as you can. And yeah, we'll go talk about that Wednesday and after. Wrap up right there.